Hi, I'm Joshua Hammond, and this is Process Dynamics and Control. This lesson is on solving differential equations in MATLAB, specifically solving them numerically. First, let's briefly discuss what differential equations are. Differential equations describe rates of change in systems. Their form is usually with some differential term, showing the change of the variable we're looking at, here f as an example, over a variable that we're changing, here t. So here we have df dt is equal to a function g of t. We'll usually see it like in this form with at least one independent variable, if not multiple. A couple examples are a differential equation of the speed of a rocket. If we were to integrate the speed of a rocket, we would be able to understand the position of the rocket. Similarly, if we have a CSTR and we integrate the rate of reaction, we'd be able to understand better the amount of product that we're getting at any given time. Finally, we'll be using the temperature control lab for much of this course. As we have differential equations that model the temperature change or the total energy change within this system, we'll be able to better understand and then better control the behavior of this system. Let's move on now to how we'll numerically integrate in MATLAB. Let's discuss briefly how we'll use MATLAB then to numerically solve our ODEs. We'll be using ode45, which is a good place to start for most ODE solving in MATLAB, as it integrates equations quickly with low computational cost and reasonable accuracy. If you notice your functions behaving odd, you may use ode15s, which is a solver specifically for stiff systems, which are systems that diverge unless we have super small step sizes. So I'll conclude down in the bottom a link to the documentation both for ode45 and 15s, as well as a table for deciding which one to use. The syntax for ode45 is right here in front of us. We have an array that's returned with t and y, and then our function ode45 with 3 arguments. ODE_fun will be the function that we're integrating, and it will be in the form of the derivative is equal to the function with t and y as the 2 primary arguments. If we're actually calling a function, then we'll need to use the @ symbol to show that we're calling an actual function rather than including the function explicitly right there. We'll also include t-span, which is the time points that we'll be evaluating at, and also y0, which is the initial value of any of the points that we're integrating. If we're going to have multiple arguments, we'll scroll down right here. We'll have ODE_fun, t, y, and then a, b, and c, which are the 3 additional arguments our function requires. To do that, on that next line, we'll create an anonymous function with that @ symbol, and then what will return, t and y, and then the actual function itself, where we'll call the function with all its arguments. Let's take a look now at 2 specific cases that will be important for us. We'll have case 1 if we have multiple integrated variables, or think of a system of interlinked equations. Here we have dx dt is equal to -y, and dy dt is equal to x, with initial conditions of both at 1. So these 2 equations depend on each other. X and y will be interlinked through this whole span, and so we'll set up an equation that works for both of them. So let's go down first to our equation where we define that. Here's our function for example 1. We have dz dt is equal to example 1, our function name, a tilde because none of these arguments require t, and so we still need to have that spot taken up for spacing wise, let's call that position, but we don't actually need it, so we use that tilde to signify that. And then z. We're going to unpack our output array, so we're going to pack both x and y into z. So we have x at index 1 and then y at index 2. We'll find our differential terms, just plugging those in, and then what we'll return is the differential terms, so dz dt, which is dx dt, and then dy dt in those same positions. You also notice that we're including it in a column vector. That's specific to this situation where we have multiple things that we're integrating, and the way we'll do that is that semicolon right there instead of just a comma or a space. That's how we denote that it's a column vector. So now if we scroll back up to exercise or to case 1, there we go. So we have our initial conditions. T-span is equal to from 0 to 10 is when we'll simulate. Our initial conditions are 1 and 1. Those need to be a column array as well, since our output is a column array. It needs to be the same shape. So now we'll actually simulate. So T and Z is equal to ode45. We're going to call our function name, example 1, have our time span and our initial conditions. And then we'll graph it down below. X is equal to all of the rows but the first column, and Y is equal to all the rows, the second column right there. And I'll actually run this and we'll look at the outputs to make sure that makes sense. So we'll see it running. We can see the output on the right with Z. We'll see that there are 2 columns and as many rows as we have time points. It looks like there's 57. So the first column is going to be our X and the second column is going to be our Y. We're going to use that colon to signify all rows and then first, or all rows and then second columns. So let's look at our graph and just make sure it makes sense for a moment. We have both of our arrays, or both of our equations, starting at initial value of 1. Our Y value is going up at about a slope of 1, and our X value is going down at a slope of -1. And we can see how those two kind of pull each other in kind of a mirroring effect. So it looks like that worked pretty well. So let's go to case 2 now, just to make sure we understand what will be important later. So there's a change to one or more inputs during the simulation. So if we have something that say we want to turn on a motor halfway through a simulation, we want to be able to simulate that in our differential equations. Here in this equation, or in this example, we'll use U. U will be our user input. So we'll say U is 1 when t is less than 5, and U is 0 otherwise. So we're going to turn it off at 5. And our initial condition is 0. And dy dt is equal to -5 plus u times e to the t. So it's going to be -5 when u is off, and then this exponential term when it's on. So it should be pretty clear when it's on and off. So again, what we'll do, let's go down to our equation, and we'll see how we made this function. Here we have our function, example 2. We have our t. We have a tilde because it doesn't depend on y. And then we have u. So dy dt is equal to -5 plus u times exponent t. It's pretty simple there. And then we're going to end, we're returning that dy dt term. Again, we have that tilde just because we don't have y in our equation, so we just keep that space open because it needs to be in the form t, y, and then any other arguments that we have. But we need to keep it consistent with the MATLAB, so we tell it that space is open with a tilde. Alright, so case 2, we're going to use n to control the length of our array. N equals 10. Create our input array. So we want this to be as long as n plus 1. And it will be 1s before 5 and 0 afterward. And then we're going to create an array y to store the results of each time slice. And we'll talk about that for a bit when we create a loop. And we'll also have a time array, which will be 0 to n, so 0 to 10, with 11 points. And that's just so we can get both 0 and 10. If we count both 0 and 10, we need 11 points. Our initial condition is going to be y equals 0, and then we're going to use this for loop. So we're going to say I is equal from 1 to n, so it's going to be all of those values at one point or another, starting at 1. And our time slice is going to be that chunk between what we're at right now and then the next point. So when we're starting, it'll be from time chunk 1 to time chunk 2. We'll return our results with t and then y, but we don't need the t, so I left that tilde there. And then we're going to call ode45. We can create an anonymous function because we have more than one input needed. We're going to call example2, which is our function name, and we're going to slice u at the value that we want. So u sliced at I. That way, each value that we're getting is the value specific to that time slice. We'll include the time slice value and our initial conditions. Finally, we'll say y0 is equal to the last value of our results. Now let's think about that for that moment. If we're simulating just from time point 1 to time point 2, our ending point will be at the value at time 2. But then for our next time slice, it will be time 2 to time 3. So we do that so that we can have the value from 2 to 3 will we'll be starting at the value at 2. Hopefully you can think that through, and hopefully that makes sense. If not, as we go through, that should make sense. And finally, we'll store our result yi plus 1. Again, we're at index 1 for that very first one. That's how I think it through. Think of that very first one. So at index 1, after we're done simulating, it gives us our value at 2. So at 1 plus 1 equals 2. So at index 2, that should be our end result that we're going to store there in a y array. And then finally, our script is going to plot that. So we can see we already plotted it because of that running before. And we have, first we have a -5 and then the exponent, so we can see it's going up. It's kind of rough because we only included one time slice at every second. If we were to include more slices in between by placing more points in our time slices, if we create more time slices I should say, then we could have a finer grid. And then at 5, so at 4, at 5 it turns on, so at 4 is the last time it's going up. At 5 we already have a slope of -5. And it starts going downward. So there's just two examples I wanted to hit of things that will be important as we go on. So let's look at the answers to those exercises now. And what we'll do just briefly is we'll just talk about the functions themselves and how we'll code those, and then we'll go to actually setting up the problem. We have exercise 1, dy dt is equal to -y plus 1. Exercise 2, 5 dy dt is equal to -y plus u. We have our initial conditions right there. Exercise 3, we have a system of interrelated equations. dx dt is equal to 3e to the -t, and dy dt is equal to 3 minus yt. And then finally, exercise 4, we have 2 dx dt is equal to -x plus u, and 5 dy dt is equal to -y plus x to the t. So what we're going to do is I'm going to go through the equations first. We're going to create those equations, and then we're going to discuss the answers. So for exercise 1, we have dy dt is equal to our function name, ODE, exercise 1, a tilde because our equation does not depend on t, and then y. And then our term dy dt is equal to -y plus 1. For equation 2, we have dy dt is equal to ODE, example 2, or ex2. It does depend on t, and how we're going to use that is rather than to provide an argument u, there's a second way we can do that. It's just a little bit less robust. If we want to change when that argument turns on, we have to come to our function. So if t is greater than 10, u is equal to 2, otherwise u is equal to 0. And then we have our equation dy dt is equal to -y plus u divided by 5. If you'll remember, our original equation had 5 dy dt was equal to -y plus u. We need to move everything but that dy dt term to the left, to the right hand side. So just the dy dt is on the left. So we're doing that right there. Example 3 now. We have our system of interrelated equations. So we're going to unpack our terms. You'll notice that the equations don't depend on x, so we're only going to unpack y, which is that second term in z, the argument that we're given as we run this. And then we have our two equations, dx dt, dy dt, and then we're returning a column vector. Remember that column vector is important with those semicolons. And then finally, we have our fourth function. We have an input and we have interrelated equations. So we have a tilde, which doesn't depend on t. We have our z, where we're going to input the equations that integrate. And then u is going to be our inputs. So let me iterate that one more time. Our z array is only arguments that are integrating, and our u is our inputs. So we have x equal to the first index of z and y equal to the second one. We return our differentials, dx dt, dy dt, again, everything on the right except for our differential term. And then dz dt is a column array with both those differentials. Alright, let's go look at how we set these up now, because that's the second end of the challenge. We can do functions pretty easy, and I always find it's easy to understand my function so that it makes setting up the equation easier. So let's go to exercise 1. We have our initial conditions and our time slice. Then we're going to call our function using the at symbol right there. We're going to return the results in the time and the y. Then we're going to add a title saying exercise 1. Normally we'd have axis labels, but here we're doing everything unit lists. So let's go ahead and run that and look at how that looks. And just make sure it makes sense. We have an initial point at 0. That's true. And let's look at our equation, just make sure the slope makes sense. Negative yt plus 1. And if we look at our graph here, we're going to have negative 0 plus 1 since we're starting at a y value of 0. So that makes sense. So we're going up about a slope of 1. And as we're approaching 1, it'll be negative 1 plus 1, so it'll be approaching 0 as y goes to 1. The slope will be 0, be approaching 0 as y approaches 1, excuse me. So there we go. That seems to make sense. Let's move on to exercise number 2 now. Exercise number 2, we have our term right there. We have our function, ODE example 2, ODE x2. And then we have our time slice. This time I just put everything in 1 just to see how we can do that. We can just put in the numbers and array 0 to 40 and let it put in its own individual time points and an initial condition of 1. Remember, on this one we use the if statement to decide what the value of u will be in that function. So let's look at how that turned out now. So we can see that it's definitely going downward. At time 10, our u becomes 2. That's what that step function right there means. That s means whenever that what's in the parentheses right there is negative, s is going to be 0. Otherwise, s is going to be equal to 1. So whenever t is less than 10, our u is going to be 0, and when it's greater than 10, our s is going to be 2. Or sorry, our u is going to be 2. S is going to be 1. So if we look at our function, we have negative yt starting at 1, divided by 5. So negative yt divided by 5 is what our dy dt should be at time 0, and it looks like it is going down. So that makes sense. And at time 10, looks like we have a negative, let's say 0.2 plus 2. So it's going to be going up now pretty steep at about 2.2, or 1.8 actually. That looks to make sense as well. Let's look at our exercise 3 now. Scroll a little bit better. We have our interrelated equations, dx dt and dy dt. In both of their terms, we're going to start at 0. I'm going to provide those arguments just with the column vector already provided there with that semicolon within it. And then we have our time points 0 to 20, and then we're going to call our function. Again, we can just call the function because it's just a function of y and t. So there's no extra arguments. We don't need to make an anonymous function. The tricky part here is that we need to unpack t and z. So let me just run it and we can discuss one more time how we did that. You can see that z has 2 columns and 77 rows. So that first column is going to be the x terms, and the second column is going to be the y terms. So if you look on the left, lines 44 and 45, we're going to use that colon to stay all rows, and then the first column. I always remember RC for two-dimensional matrices or arrays. So rows, then columns, RC. So in the rows portion, we're going to use all the rows, so that colon, and then first column, y, we're going to use second column. And we're going to plot that right there. You can see they're right on top of each other, so we're using the 2 symbols right here. We have approaching 3, which seems to make sense. 3 to the negative t, so as t gets large, for x, for example, the slope's going to be approaching 0, and so that makes sense to me. Move on to exercise number 4 now, the last one. We've almost done it. So we have an input and we have 2 different arrays. So let's go ahead and let's remember what our function looks like. I think that makes sense here. We have t, z, and u, where z is what's being integrated and u is our user input. So exercise 4. I like using n when I'm doing arrays, so I can change the length of the array just by changing n. So we're going to do n is equal to 30. We're going to create our u array, our input array, which is going to be zeros from 1 to n plus 1, so 1 row and n plus 1 columns. And then from 6 to the end, that's going to be equal to 2. We're going to initialize our other storage arrays, so both x and y, we want to create a different array separate from our ODE int. That way we can store just the ending value from each time slice. I'm going to make those zeros just so we know something's up, like there will be zeros, and if something's working, they won't be 0. And then z0, our initial conditions, is a column array or column vector, since our output of z, or our output of the function, will be a column array as well. Finally, we have our time, which is what we'll iterate through. We'll get our time slices, which is from 0 to n with n plus 1 points. Like I said before, the nice thing about using n here is that if I wanted to make it 50 long, I just have to change on line 53, n is equal to 50, and that'll all work. Let's go to our for loop. For I, from 1 to n, we'll do our time slice. Again, I'm just going to imagine at time slice 1. So we're going to slice from time 1 to time 2, and it will put some points in between for us. Our time and our z will be returned from our function, and we're going to create an anonymous function with that @ symbol, where we're going to return t and z, and then our function itself, which is our function called with u indexed at I, so that each element within u is exactly what we want. We then have our time slice and our initial condition for each iteration. We have z0 identified on line 61, so we know what it is initially. And then after that, we're going to work from that. Finally, so we can see that at z0, and then the last row, both columns, that's kind of a reversal of what we're saying up here. Let's go right here. This is what z looks like on a different problem. If we take the very last row of that, both columns, that will be the initial conditions for the next round, or for the next iteration. So we're going to save those results, and then we're going to save x and y's value in the x and y arrays. Finally, we're going to plot it. So let's look at how that works. So there we have them both going up at different rates, but they both have a limit of 2. So there you have it. I hope you'll especially just remember, let's go back up to these two cases. What's very important about this lesson is to first remember how we're going to integrate multiple integrated variables. And that's using an array that we pack both those results into. I usually call it z, since we're using with x and y a lot of times. And then second, how to use for loops to iterate through our time slices so that we can change inputs in any given moment in our time arrays.